All right, so the last example set us up for this idea of testing hypotheses. And we actually saw this in our example on Tuesday when we started looking at that, what was it, the babies choosing the helper, the hinder blocks in that one example. So what we're going to be doing is we're going to be testing two competing claims, just like we did in the helper hinder example, right? Either there's absolutely nothing going on, this is completely due to chance, or there is something causing the babies to choose what we consider the helper toy. So we have to set up these hypotheses. The first one is the null hypothesis. This was, in our baby example, the idea that this was just chance, that there was nothing going on. Most of the times you can actually kind of consider this a null hypothesis as chance world. What if you're wrong? What if there's absolutely nothing going on? What would it look like then? So that's our null hypothesis. It is the initial belief. It is your starting point. Our alternative hypothesis is usually what we want to prove. Now, we are going to make these a little more formally than we did in the baby example. In a formal sense, what we'd want to say for our null hypothesis, we denote that null hypothesis with an H and a little tiny subscript of 0, because it's our starting point. It's our initial thing. I'm sure you've seen this notation before in whatever other math classes you've been in. Usually you'll see like a P with a little 0, and you call it like P naught. And that's your initial starting point for a population, or you might have seen it for, like, I don't know, interest problems. Sometimes you'll have your initial principal in there. So that's what that little 0 is for. And this is going to be that P is equal to some value. We need the equal sign because that's what lets us set up where our actual mean is and actually do any of our problems. We need an equals. So our null hypothesis is always about P equaling, and then we will use some null value, some P with a little 0. We don't have to use this notation so much, because now we're getting really confusing. We're going to have P, P hat, P naught, and eventually a P value, and life just gets confusing. But this is basically, P naught is our test value, basically our proposed value for real P. So it's not real P, but it's our guess at what real P is. Our alternative, the thing we want to prove, is we denote with an HA. And there are 3 possible alternatives for us to look at. We can be dealing with, we want to see if it's greater than whatever our hypothesized value was, which we call a right side test. We could be doing, we think that it's actually less than whatever our hypothesized value was. Or we could be saying, we think it is just not equal to. I don't care how it relates to the original value. I just want to show you that that original value is wrong. So these are our 3 possible setups for alternative hypotheses. We will have nice keywords letting us know which one we're interested in, and we should be pretty good at that coming out of the normal distribution section, where we got really good at saying which side of the curve are we shading. And essentially this is still telling us which side of the curve we're shading. So we're using the same keywords: increase, more than, things like that. So before we really get into the steps of a hypothesis test, I wanted to give us a way to relate our hypothesis testing to 6.1, because we already related the hypothesis testing to 6.2 in that last example from 6.3, and now we're going to kind of go back to our sampling distributions, essentially do a little bit of what we did in class when we talked about the helper hinder question. So I have this ridiculous example. Suppose you and your roommate have a special coin to decide disputes, including determining whose turn it is to take out the trash. All right. So you want to examine if the coin is fair and believe it gives out a larger proportion of heads than it should. So you think this is not a fair coin. It seems like you are taking out the trash a lot more than your roommate. Seems to be coming up heads a lot. So you think there might be something funky going on with the coin. You decide that you know some stuff about the sampling distribution of proportion, and you're going to use it. See if he's cheating. So we flip the coin 20 times, and we get out 12 heads. We basically do one of the silly experiments we're always doing in class. So if the coin is fair, what do we expect the true proportion of heads to be? Well, If it was a fair coin, it'd be 50% heads. What did we get out as our sample proportion? Well, 12 over 20 is 60%, right? Here, I'll even write 12 over 20 because someone will be like, where did you get that? Now, C says, this is exactly what we did in the helper hinderer question. Is this evidence for what we want to prove? Does this seem as what we got something that is rare, like very rare, kind of rare, or not at all rare? And this doesn't look like a whole lot of evidence. 12 out of 20 is not that far from our expected of 10 out of 20, right? So, not really. Right? I mean, 14 out of 16 babies was unusual, but like 10 out of 16 wasn't that unusual. We had a lot of people who got 10 out of 16 on their rolls of the dice. So you go, Well, first thing we gotta check is, are we able to use the approximate normal distribution to be able to play with this example? So, are the trials independent? Yeah, we're flipping a coin. Duh. If sampling was done, the method, well, we didn't do any sampling. We flipped a coin, so we're fine. Actually, I'll write, instead of a check mark here, maybe an NA. Same with the next one. If sampling we didn't do any sampling, we flipped a coin. All right, last one. The sample size must be large enough, so a rule of thumb, for our rule of thumb, that our expected number of successes and failures will be greater than 10. Well, we know real P in this case. So N times our real P is equal to 10, and N times our real Q is also equal to 10. So we can barely use our rule of thumb. But that's okay, as long as it's allowed. So if that's the case, it says, well, what are the mean and standard deviation for the sample proportion? So we're going to go back to our formula sheet, because remember, our formula sheet has a section for sample proportion stuff. So sample distribution for a sample proportion, this is the mean and standard deviation I'm going to use. So if we were doing this, what we expected for our mean of our sample proportion should have been centered at the real P. So we expected 50%, we got out 60%. But how much variability is there away from that 50%? Well, whatever the heck 0.5 times 0.5 over 20 is. Which, I don't know in my head, so we've got 0.1118. All right. So based on that standard deviation, 0.6 is totally not unusual, right? If we added one standard deviation to this, 0.6 is within one standard deviation of the mean. It's in that middle 68%. So we're already thinking, doesn't look like I have enough evidence to prove that my roommate's cheating here. It doesn't look like this is something terribly unusual that's happening. But we're going to go ahead and draw our curve here. So if we draw our curve, we know what should have happened, or what our mean value is 50%. If we wanted to, we could even make some cute little bunny hops based on this 0.1118. I'm just going to kind of think about them as I put in my 0.6. 0.6 is not even one bunny hop away, not even one standard deviation away from the mean. So this is what we got. That is a terrible looking 6. 0.6, 60%. Now, we want to shade the probability of getting a sample proportion at least as large as the one we got. Because what we got was 0.6. But if we'd gotten anything worse than that, it also would have been evidence for us showing that there's something weird and it's giving out more heads than we want. So we're going to shade this direction because we wanted to show that our coin is giving more heads than we expected. So in this case, it says, well, let's go ahead and calculate a z-score and a probability, just so we can have both pieces of evidence. We know z-scores also tell us how unusual something is. So we'll do that in 2 steps. First one we'll go ahead is do our z-score. This is our observed, right, minus our mean divided by our standard deviation. So 0.6 minus 0.5 all over that 1118. We already know based on our drawing and based on thinking about that standard deviation that this is less than 1, but we'll get an actual number for it. Come on, there we go. 0.8945. So definitely not unusual based on that z-score. It's not even one standard deviation away from the mean. If we wanted to, we can also look up this probability. We have lots of ways we could do that. We could use our z-table because we do already have a z-score. I know a lot of you in my third class will want to do that since you guys are old pros at stats and you like that method. For the rest of us, we'll probably be finding that probability by using normal CDF. 0.6, crap ton of nines, 0.5, 0.1118, or since we have a z-score already, we could just do 0.8945, crap ton of nines, and then we could put in 0, 1. Either of these should give the exact same value. It doesn't matter. So I'm just going to go ahead and use the z-score because it'll be quicker. Oh, do I have the wizard off? Good, no wizard. So 0.8945, crap ton of 9. Since I don't have my wizard on, I don't even need to put in the mean and standard deviation since I use the z-score. But this is our probability. Our probability is 0.1855. So there's a little over an 18% chance, right? An 18.5% chance that this would happen. Almost a 1 in 5 chance that this would happen. So in this case, we don't really have evidence. We know. Unfortunately, we can't say the coin is behaving unusually. We observe something that'll happen 1/5 of the time. So what we had was something that wasn't very rare or unusual. So it doesn't seem like the coin is behaving differently than a regular coin would. So what if I'm really I'm really convinced this coin is not fair. So what I end up doing is I say, well, you know what? I got nothing but time. I hold a grudge. So I'm going to flip this coin 200 times. And when I did that, I got 120 heads. Now remember, this still gives me a p hat, right? This n is equal to 200, x is equal to 120. My p hat here is still 60%, but this is just like that Kahoot question back from probability, which is more unusual. 2 out of 3, 20 out of 30, or 200 out of 300. So now since we've increased everything tenfold, this might actually change things a bit. So let's go ahead and do all that sort of work again, thinking now about 200 as my sample size. So first thing we want to do is we want to look at our distribution. The mean of our p hat is still 0.5, right? That hasn't changed. Still centered at 50%. What changed is how spread out everything is away from that mean, right? It's a lot harder. Most of our values should be around that 50%. Because we're starting to get to the end of that. Remember this thing where we did, this thing where we, our law of large numbers where we started approaching the real value. So let's see what happens to our standard deviation. Formula is still p, q divided by n. So we're still using the real deal p of 0.5, assuming the coin is fair, right? And our n is now 200 instead of 20. So we're going to end up with a much smaller standard deviation than we did in the last problem. And to see how much smaller, let's just bring this back up. I'm going to go ahead and just bring back the old calculation because I am lazy. So I'll change this, delete, to 200. So now we have 0.0354. Now 60% is over 2 standard deviations away from our mean, right? If we were to draw our cute little picture, still centered at 0.5, but if you think about those bunny hops now, we're at 0.53, 0.57, 0.6 almost, right? So our actual value of 0.6 is now way over here. Almost 3 standard deviations away from the mean. So you go, oh, crazy. This is going to be a much different question. Now 0.6 is much less usual. let's go ahead and see how it changed our z-score and how it changed our probability. So if we go to get our z-score, x minus our mean, right, our observation minus our mean divided by our standard deviation. We can visually see it on the table, but now let's figure out exactly what this is. I don't know why I'm doing this in my calculator when I can do that in my head. Now our z-score is 2.82. I guess I could give you more decimals. 49. So our z-score is much, much larger, and it is right next to our very conservative cutoff of 3 being unusual, but it's past our other cutoffs of 2.52. So we are going, ooh, way, way, way more unusual than what we saw before. And if we wanted to find out the actual probability, well, we could do our normal CDF, whichever one you wanted to use. This time I'll use the actual values just to do it differently. So if I did my normal CDF here, oops. Our lower bound was the 0.6, upper bound was crap ton of 9s, and then I would use the mean and standard deviation we found, 0.5 and 0.0354. 0.0024. I've already forgotten it. I don't know why I didn't write it down. 0.0024, I think. Yes. All right, so now, is this something that's very rare? Yes. This would make me think the roommate was cheating. Getting out 60% heads on 200 rolls of the, or flips of this coin is very, very unlikely. So there's two options, and that's the idea of hypothesis testing, is we start out with two ideas, and we basically say, I think I have to set up the null hypothesis later. Sorry, I'm like cheating. I should have paused before I did this. Yeah, jerk. But it's fine, I'll do it here. We basically set up a null hypothesis, and the null hypothesis is the thing we could actually test. We can actually pretend that this is a real coin. We need the equal sign. So our null hypothesis here is that it is a fair coin. It's a 50% chance that you get heads. Our alternative hypothesis is that it's not a fair coin. And in fact, we have a direction that we think it's not fair. We think he gives more heads than tails. So this is our alternative. This we can't test because we don't have a set P. There's no way to actually do that. But the first one we can, and that's exactly what we just did. We said, okay, well, if this is true, if this is the real mean, and that's the thing we use in our standard deviation, if that's true, well, there's a 0.24%, less than 0.25% chance that we get out 60% heads in 200 tosses. So what does that lead us to believe? It leads us to believe that either we are incredibly lucky and just got a ton more heads than expected, or this original assumption was wrong. It's sort of like what we call a proof by contradiction in mathematics. I'm going to assume this is true and then go through all this work. And if at the end it doesn't work out, then I'm shown the only other possibility is that the coin isn't fair. That it really, the mean should have been something way higher than 50%. So I know this is a long video. Thank you for sticking with it. But I really wanted to show you guys how 6.1 is really the heart of what we're doing here in 6.4.